Okay, so now we are recording. Right, so are there any questions or concerns regarding anything we've discussed so far or regarding assignment 1? Right, so assignment 1 has been posted and it is due in, you have a total of 10 days. So it is due on 15th February at 11 p.m. Okay. And I've also posted collaboration rules and what exactly does it mean to collaborate in this course. So please read the post on Piazza carefully and make sure that you're following all of the guidelines. And if you have any doubts which are not addressed, then please direct those to me or to the TA and we will resolve those doubts. Okay. All right. So if there are no specific questions or concerns, let us begin module 2. I'm calling it geometry and simplex. Okay. We will begin with focus on geometry and we will eventually move on to other topics and eventually to the simplex method and probably come back to geometry. All right. So I'm going to write down a particular linear program for the sake of example. Let us call it linear program 1 for this lecture. Okay. So we are going to maximize an affine function, which basically means a linear function plus a constant. In this case, it is just a linear function. The constant is 0. Subject to certain linear constraints. Okay. And here are the linear constraints for this example. Okay. So we have a total of 5 constraints. Let's just call them 1, 2, 3, 4, and 5. And we have 2 variables. So 5 constraints and 2 variables. Okay. All right. And let's remember the general structure. Notice that if you have any equality constraint, you can write it down as a less than equal to and a greater than equal to constraint, right? If you have alpha x1 plus beta x2 less than equal to gamma, you can just write down 2 constraints, alpha x1 plus beta x2 less than equal to gamma and greater than equal to gamma, right? So in other words, I can write any linear program as in this form. So for the sake of geometry, we are going to focus on this form. Okay. And this includes all of the constraints. So even the non-negativity or non-positivity constraints like these last 2, they are also taken care by this format. Okay. And I'm writing maximize because if it was a minimize problem, you would just flip the sign and make it a maximize problem, right? So this is a pretty generic form of any linear program. In particular, all linear programs can be written in this form. Okay. And this form is simpler to think of when we are discussing geometry. We don't have to distinguish between the different kinds of inequalities and constraints. Okay. If you have a greater than equal to, you can just multiply both sides by -1 and turn it into a less than equal. Right. So the point I want to make is any LP can be written in this form, right? Are there any questions or concerns? But let's not worry too much about these minor observations. What I want to focus on today is what do all the solutions to this linear program look like? Okay. And in fact, we are going to call them feasible solutions. That is the standard terminology. So for any given LP, a feasible solution is a vector x bar that satisfies all of the constraints. Okay. Can someone give me a feasible solution to this system simply by inspection?
1, 1.
1, 1. Great.
Even
So
0, 0 works, I think.
yes, that also works. For example, 0, 0, 1, 1. I think 1, 2 and 2, 1 are also feasible solutions in this case. And there are many other feasible solutions. Okay. Can you give me a solution that is not feasible?
10, 0.
Sorry?
10, 0, sir.
10, 0, right. That would contradict the first constraint already, right? 20 is less than equal to 9. So 10, 0 is not a feasible solution. Okay. All right. And what I want to focus on is I want to look at all the feasible solutions and try to understand what does this look like in a geometric sense. Okay, so that is going to be called the feasible region of any LP. It is the set of all feasible solutions. Okay, in other words, it is all x bar such that x bar is a feasible solution. So what does this space look like? And I just want to plot this for this example. You can see that I've deliberately chosen 2 variables so that we can actually draw things on the paper, right? In the plane. Okay. So notice that these things have nothing to do with the objective function, right? The objective function is basically irrelevant for today's discussion. Right? What is the objective function? It is this, what we are maximizing or minimizing. Okay. Good. Before we completely discard the objective function, let me put down some definitions. So in this particular problem, we are interested in maximizing the objective function. So we want to find a feasible solution that maximizes the objective function. So those feasible solutions are going to be called optimal solutions or optimal feasible solutions. Okay. So an optimal solution is a feasible solution that attains, or maybe I need another definition. Right. So for a particular feasible solution, you can define the value of that solution, which is going to be the value of the objective function evaluated for that feasible solution. Okay. So for example, if you look at 1, 1, right? What is the value of 1, 1? It is x1 plus 2x2. So that will be 1 plus 2 equal to 3. Right? So the value of 1, 1 is 3. So the value or objective value, generally I'll just say value, of a feasible solution is the value of the objective function attained at that feasible solution. Okay. So for example, in our case, the value of 1, 1 is equal to 3 because it's x1 plus 2x2. Okay. And the optimal solutions are precisely those feasible solutions that attain the maximum value for a maximization problem or the minimum value for a minimization problem. Okay. So we don't know what a optimal solution for this particular LP is, but let's not worry about it. We will eventually find it. Okay. You can also say if a solution is better than another solution for a maximization problem, a solution would be better, a feasible solution would be better than another if it attains higher objective value than the other one. Right? So for example, for 1, 2, what is it? It is 1 plus 4, 5. So value of 1, 2 is 5. And so in that sense, 1, 2 is better than 1, 1. Okay? You get the idea. Okay, good. So let's focus on the feasible region now. So I want to just copy paste these constraints and focus on them and not worry about the objective function. So let's see. That is a bit too far on the right. Okay, fine, whatever, doesn't matter. Okay, so let's look at our constraints. And let's try to figure out what the feasible region looks like. Okay. Okay, so since it's just two variables, we can actually draw things, which becomes difficult beyond some number of variables. So let's see. Okay. All right, so I'm going to treat each of these half points as a 1 unit. Okay. Let's put a few here. All right, so let's look at the first constraint. In fact, I want to plot the line 2x1 plus x2 equal to 9. Okay. So let's find out 2 points. So this is going to be our x1 axis and this is going to be our x2 axis. If I put x1 to be 0, x2 is 9. So 0, 9 is one solution. And 4.50 is another solution to this equation. Right? And those 2 points should be sufficient to plot the line. Okay. So where is 9? 1, 2, 3, 4. Okay, let's see. 0, 9 would be. So this is the point 0, 9. Okay. And 4.50. 1, 2, 3, 4. Okay, so it's going to be here. This is going to be the point 4.50. Okay. And this is our constraint when you look at the equation corresponding to it. Right? But what about the actual constraint, which is a less than equal to and not an equation? Can someone tell me which are all the points in this plane that satisfy this constraint?
Below this line.
Below this line. You mean in some sense to the left of this line. Right. So there are two, this line breaks the plane into 2 parts. And all the points that are to the left or to the side of the arrow that I've drawn, those are all the points that satisfy the first constraint. Okay. Good. So whenever you have a linear equation, what you're basically doing is you're breaking the space into 2 parts. Those that satisfy and those that do not satisfy. And this is going to be called a half space. Okay. So H1 for this problem is going to be all of the vectors x1, x2 that satisfy the first constraint. And all of these points are referred to as a half space. Okay, I'll write down formal definitions later, but you get the point. In fact, yeah. So H1 is a half space. Let's plot down the next half space. So this is the first one.
Sir, I have a question.
Yeah, go ahead.
Sir, after we draw the line, how will we decide which direction to be?
Sorry, I can't hear you.
No, my question is, can you hear me now?
Yeah, it's still a bit
My
low,
question-
but I can hear you.
Yeah, my question is, after we draw the line, how will we decide the direction of the graph? I mean, is it towards the origin or?
Right, right. So you tell me, in this example, how would you decide actually? That is a good point. In this
I mean,
particular example, yeah, go ahead.
My initial idea is substitute origin into the equation.
Right, exactly.
And if the
Exactly.
origin satisfies, it will be towards the origin.
Right, that is in fact the correct way of doing it. Of course, the line could go through the origin, and then you could use any other arbitrary point that is not on the line.
But yeah, but I think this will be easy for the 2 dimension. But if the equation has like some n dimension, then
Turns out in n dimensions we can't even draw and make a direction clearly, right? I mean, we can't even visualize it. But it's the same idea. It is still going to break the space into 2 parts, and the important property of half spaces is a thing called convexity, which we'll talk about later.
okay.
Right? But For the sake of visualization, we are just going to look at 2D, and you can probably do 3D, but we are not going to do that in the lectures, right? But the same ideas go through even in higher dimensions.
Okay, but in higher dimensions, suppose if there is no zero in our space,
Right.
then how will we decide the direction of that particular sequence?
Just take any arbitrary point, right?
Okay.
So, I mean, the definition of a half space is simply this, right? So the
Okay.
definition still works no matter how many dimensions you have, right? So I just want to give you a geometric intuition, and the geometric intuition, to be very honest, beyond 3 dimensions, it doesn't even make much sense,
Okay.
right?
Yeah.
Because we can't really visualize it. Luckily, a lot of the geometric intuition that you gain from the 2D and 3D cases can be converted into precise mathematical formulations, and many of them work out for all dimensions. And one of those things is convexity that we'll be talking about later.
Okay. Go.
Right? So it is still going to be a convex set. If you know what that means, that's great. Otherwise, we'll talk about it formally and we will be discussing things vigorously later. Yeah, does that make sense? Right, so the formal definition is just all the vectors that satisfy your constraint. And it's basically going to break your space into 2 parts, those that satisfy the constraint and those that don't satisfy the constraint, which is basically why it is called a half space. Does it answer your question?
Yes, yes, I got it.
Okay, great. All right. So now I want to draw the second constraint and the corresponding half space. So, well, let's look at this one. X1 plus X2 equal to 7. That's very easy, right? 0, 7 and 7, 0 are 2 points. So let's just take them. This is 0, 7 and this is 5, 6, 7, 0. And let's draw this line. Okay, great. So this is our second constraint, and the direction, well, the origin is on the left side or on the direction that this arrow is pointing. So our half space is this line and everything that is on the left side of this line in the direction of the arrow that I've drawn. Okay, so that is our H2. Let me actually call them H1, H2. This is H1. This is H2. Great. Let's look at the third one. Minus x1 plus x2 equal to 5. Minus 5, 0 is a solution and 0, 5 is a solution. And minus 5 is here. And 0, 5 is here. So let's draw this line. Okay. And the point 0, 0 satisfies the constraint. It's on the right side. So this is going to be our half space H3. And H4 and H5 are very easy. They are simply the 2 axes. And basically you get the top right quadrant. So the fourth half space is this, and the fifth half space is this. Okay. And what are our feasible solutions? Can someone tell me what are all the feasible solutions with respect to these 5 half spaces? In a set theoretic sense.
All
Yeah.
the area enclosed by these lines in the first quadrant.
Exactly. But can you give me a set theoretic way of looking at it now?
Okay, I'm not getting a set theoretic way.
Now think about it. So your 5 half spaces, they are sets of points that satisfy the 5 constraints respectively, right? Now I'm looking at all the points that satisfy all of the constraints. What will that be set theoretically? With respect to, yeah, intersection, exactly. Right? Does everybody agree? So the feasible region of our LP1 is simply H1 intersection H2 intersection H3, 4 and 5. Right? So let's draw this, let's shade this area just to get an understanding. Notice that this is exactly this area that I am shading with a red color, including the boundaries of this formed by those lines. Right? So this is our feasible region for this particular problem, LP. Are there any questions or concerns? Does everybody agree with this point? Right? It looks like a convex polygon. That's not a coincidence. Turns out convexity is something you get for free. You probably have seen convex polygons in some context before. This is basically a convex polygon. If you're not familiar with convexity, don't worry. We'll talk about it rigorously sooner or later in this module. Okay, good. So let's put down some definitions to make all of this a bit more rigorous. I wanted to start with an example so that you can visualize what's going on. Right. All right, so a half space. A half space in Rn, so we could be in n dimensions, it doesn't matter, is any set of vectors that satisfies a particular linear inequality. Okay. Yeah. So it's going to be a linear inequality for the variables x1 to xn because we are in n dimensions. In this example, we were in 2 dimensions and we were just looking at 2 variables. Right? And okay, so basically it's something like if you want it a bit more in symbols, let's say it's all of those vectors in Rn that satisfy A transpose x bar less than equal to beta, where beta is some real constant and A transpose is some real row vector. Remember, our x bars are always going to be column vectors, and for the row vectors we are going to use transpose. Okay, that's just a notational convenience. Okay, so that's basically what a half space is.
Sir, can you explain again about the x bar? Why is
Sorry?
it x bar and not x? So can you explain again about x bar? Why it is x bar and not x?
Well, you can write x here, it doesn't matter. If you use x in both sides, it's fine.
Okay.
So it will be okay. It's just that generally when I am writing an inequality, I'm using x as a variable, but here x bar is all possible feasible solutions. So it's all x bars that satisfy that particular inequality. But yeah, it doesn't, it's just a matter of notation.
Okay.
Right? Okay. Okay. So that's what a half space is. And we saw 5 particular half spaces in this example. Right? And the intersection of 5 half spaces or the intersection of any finite number of half spaces is actually not a new thing. It's not something that was started with optimization. It is something that has been studied from very old times in mathematics, generally in 2 and 3 dimensions. And there is a term for it, it's called polyhedron. And that comes from ancient Greek mathematical literature. So a polyhedron in Rn is the finite intersection sorry, it is the intersection of a finite number of half spaces. Okay, and I like to say a bit about the etymology. So this is not a new concept. Optimization is fairly recent, but polyhedrons and polygons, these have been studied for a long time. Right? So it comes from the Greek, and it means many polyhedron sides. Okay, generally they refer to only 3D objects as polyhedron, but we are going to be considering it in Rn. Why not? All right, and notice that, right? And in 2D, this is the same as polygon, right? So you definitely heard of polygons, and in 2D, this is basically convex polygons. And just to be clear, the plural of polyhedron is not polyhedrons, but it's polyhedra. So polyhedrons have been studied in mathematics for centuries, maybe millennia, I'm not sure, right? But the fact that the feasible solution of any LP is simply the intersection of a finite number of half spaces, as we saw in this example, and therefore the feasible region of any LP is nothing but a polyhedron. So the observation is that the feasible region of any LP is a polyhedron, right? And what is a polyhedron? It is the intersection of a finite number of half spaces. Remember, when we defined linear programs, we required the number of constraints to be finite. You can't have infinitely many constraints. So I have a question. Can someone give me a simple example in 2D or 3D of something that is not a polyhedron?
The arrow shapes are.
Arrow shape. Yeah,
A circle.
like this. Sorry, what was the other one?
Circle.
Circle. I actually was looking for something along those lines because it is a convex object. If you have read Convexity, I'm pretty sure you've seen that circle is a convex object. It satisfies most of the properties of polyhedron, but it's not a polyhedron because you will need infinitely many constraints to describe a circle. Okay. For that matter, even an arrow shape like this is not a polyhedron. A sphere is not a polyhedron, etc. Because a sphere will also require infinitely many constraints, and that's not allowed. Okay. Good. All right. Are there any questions or concerns at this point?
Sir,
Yeah, go
I
ahead.
understood why circle and sphere are disqualified for polyhedrons because of the infinite. But how is arrow disqualified by being a polyhedron?
Right. Right. Okay. Good point. This, at least the way I've drawn an arrow, it's, I mean, generally, I guess this is what the person meant, right? Yeah. So one way to see it is to show that an arrow is not convex. But we haven't discussed convexity. So are you familiar with convexity?
Yes, sir. I mean, some object where you draw the line inside 2 points and all the line joining the 2 points should be inside the closure of
Exactly. If you draw any line segment, if the two ends are in the object, then the whole line segment should be in the object, right? So I'm not going to write down the formal definition right now because we are jumping a bit ahead. But here you can see that this line segment in red color, the 2 points are in your shape, the arrow shape that I've drawn, but the points in between are not in it. Do you agree?
Yes, sir. Yes, sir.
Right. So we will be proving later that all polyhedra are convex objects, and therefore that would imply that this is not convex. Right?
Yes. Yeah, got it.
So the short answer for now is that it's not convex, and later we will show that polyhedra are convex. And we will also look at convexity formally and define everything. Okay. Good. All right. So that's good. There is one more thing I want to talk about. Okay. So notice that in this particular example, the polyhedron we have, in fact, it's in 2D, so it's a polygon. It is bounded on all sides. On every side, you see a boundary, right? Vaguely speaking. Can you remove one of the constraints so that this bounded property is lost? Can someone suggest what constraint can we remove so that we don't have a boundary on one of the sides?
We could remove x2 is greater than or equal to 0.
Which one?
We could remove x2 is greater than or equal to 0.
Right. We can remove this one. X2, is that true?
No, sir. X1 would do it, I guess.
Right, because if you remove x2 greater than or equal to 0, actually, wait a second. Yeah, you're right. Actually, x2 also works. You're right. Sorry, I think I did not see that. Right. If you remove x2 greater than or equal to 0, for example, right?
So then H3 serves the purpose, right? H3 will still bound it, make it bounded. H3, that is, I'm not sure which one it is, but yeah.
If you remove h2, like you have the one by x1 greater than 0 and the minus x1 plus x2 less than 5, which will bound it. So only x1 greater than 0 will work.
That's right. Right. So if you remove x2 greater than or equal to 0, so let's make it very clear. I don't want to skip it because even I'm having a slight difficulty in visualizing. Okay. So notice that x1 is making sure that everything is on the upper half, right? In the upper half with respect to the x1 axis, right? So if you remove x2 greater than or equal to 0, I think if I'm not mistaken, you get this extra area that I have shaded. Is that correct?
Yes, sir.
Right? But you are still in a bounded situation. You are still bounded by all the other lines that have been drawn.
So is that x2 equal to 0, sir?
X2 equal to 0 is this line, right?
Okay, sorry. I think is that the x-axis is
I think
x2
I've
greater
made
than
a
or equal to
mistake.
0.
Yeah, I think I've made a mistake here. Okay, so right.
Oh yeah, right. The x-axis is the x2 greater than 0. So
Right.
that should be enough.
So x1 at least 0 is actually h5. Right. Okay. So yeah, it's very easy to get confused here. This would be h5 in fact. Right? And this would be h4. So that is the reason for all the confusion. Is that correct? H5 is the area where x2 is at least 0. Remember, x2 is our second variable and x1 is our first variable, right? So I had mixed up h4 and h5. And now if you think about it, if you omit x2 at least 0, then you actually have an unbounded situation, because all of the area, give me 1 second. Right. If you remove the last constraint, then you will get all of these points. Right. So this is the feasible region if the constraint 5 is omitted. Okay, because now we are also allowing x2 to be negative. Okay. I wanted to erase this line here, but it's too close to the other line. Okay, I got it. Are there any questions or concerns? So if we remove the last constraint, we actually get a feasible region that is not bounded on a particular side, right? And when you have a bounded polyhedron, it's also called a polytope. I want to let you know, because you might see in the literature polytope many times. And what it really means, it's a polyhedron that is bounded on all sides. So there is no direction in which you can keep going on. You can make this formal, but it's not too crucial for the course. I just want to make sure so that when you look at the literature, you're not confused by the two different terms. Okay. So a polytope is a polyhedron that is bounded. And I'm going to put bounded in double quotes here because we are actually going to use the terms bounded and unbounded in a different context, in the context of the objective function. So that's not too crucial, but I just want to make sure that you're not confused by these terms, as I was as a master's and PhD student. Okay. So in particular, there is no direction without a boundary. Right? And I'm not making things formal because, as I said, it's not really crucial to the content. Okay. So if you look at this example, for the first linear program, what we got is actually the red area, which is bounded on all sides. And that is a polytope. It's a polyhedron that also happens to be a polytope. But if you remove the last constraint, you actually get the entire green region, and now there is no boundary on that side. You can always keep going in this direction and keep finding more and more feasible solutions, right? And that is a polyhedron that is not a polytope. Okay, so this is a polytope, right? But if you remove the last constraint, this one is a polyhedron that is not a polytope. Is the difference clear? Are there any questions regarding this discussion about polyhedron versus polytope? Okay. So polytopes have been also studied for a long time. In fact, generally, when people studied polyhedron, they were actually referring to polytopes back in the day. But now polyhedron is used a bit more generally. Okay. So polytope comes from German. That just means many surfaces. Right? So if you think about some 3D objects like the cube, that is a polytope. Right? Okay, good. All right, so we will generally be sticking to polyhedron. Okay. So we won't distinguish in most cases whether the polyhedron is bounded and is therefore a polytope, or whether it is it has some side where you can keep going forever, right? So that would be unbounded. Okay, but we will not generally differentiate between these two cases. Good. Notice that all of our discussion regarding the feasible region has nothing to do with the objective function, right? The feasible region does not care about the objective function. All right. Can there be an LP which has no feasible solution? Can you give me an example of an LP that has no feasible solution?
Yeah, like the intersection is an empty set.
Sorry?
If the intersection of the
Right.
half spaces is an empty set.
Exactly. So if it has no feasible solution, the intersection of the half spaces would be the empty set. So can we get a quick example here? Can we figure out two half spaces whose intersection is empty? Not among these five. Between these five, if you take any two, you will get non-empty intersection, right? So you can't take any of these five half spaces. I mean, you can take one of them, but you need another half space, which has not been listed here. So can we find this? Yeah, go ahead.
x1 plus x2 less than equal to 5 and x1 plus x2 greater than 6.
Right, sure. Simple example, right? So x1 plus x2 less than equal to 5 and greater than equal to 6. Right? Clearly, you can't find any x1 and x2 which will satisfy this, both of these, right? And in particular, you can draw the half spaces and see that the intersection is empty, which is exactly what it means to not have any feasible solution. So an LP has no feasible solution if and only if the intersection of all half spaces corresponding to those constraints is the empty set, right? And notice that the empty set, as per our definition, is always a polyhedron. The empty set is a polyhedron in any dimensions. Okay. Good. What I would like you to do as a do-it-yourself exercise, it's quite easy. I want you to add one constraint to our LP1 example so that the new LP has no feasible solutions. Okay. Add one more constraint to LP1 to make it infeasible. Infeasible LP means one which has no feasible solutions. To make the new LP such LPs are called infeasible. Okay. In particular, the gist of this lecture, which is almost over now, is that you can classify all LPs into two: feasible and infeasible LPs, obviously, right? And one of the important decision problems that we will be discussing over the course of this module is to decide whether a given LP is feasible or not, right? So here is a decision problem whether a given LP is feasible. So can someone quickly tell me whether this problem is in NP or co-NP? Which one is obviously easier?
NP should be easier, sir.
NP is easy, right? You can convince anybody that a given LP is feasible because there exists a feasible solution. How you find it is not the point. Great. So it is in NP, and turns out that it is also in co-NP. But that is something we will be discussing later. It's actually a deep result, and it is also related to duality, which we'll be discussing later. Yes, later. So there are actually ways. There is always a way to convince someone that a particular LP is infeasible. So you can actually convince someone that a particular LP has no feasible solutions, right? And clearly, philosophically, that is harder than convincing that there is a feasible solution. Okay. So that's all for today. Just to give you a quick idea of what we are going to do next. We are going to consider feasible LPs, and we are going to further classify them into two possibilities. That is going to give us the fundamental theorem of linear programming, which says that all LPs can be classified into three possibilities. And for all possibilities, all of the three possibilities, we will be seeing certificates. But anyways, all of that is coming up. So that's the end of today's lecture. But if there are any questions or concerns, I'm here for another 10 minutes. So okay, so I'm going to stop recording.